Hi, everyone. So we don't usually think about our drinking water on a daily basis. We only usually think about it when instances like Flint, Michigan's lead contamination came into the news. Just 4 hours east of here, we also have a similar issue in Hoosick Falls, New York. What they found contaminated in their drinking water was PFOA. Now you're definitely asking, what is PFOA? PFOA belongs to this large class of tens of thousands of fluorinated substances called per- and polyfluoroalkyl substances, which I will refer to this point as PFAS from this point forward. These PFASs have fluorines on their bonds, which allows them to be very strong and very stable. This also allows them to have very strong properties and preventing them from degradation. And as a result of how they're structured on this molecule, they also have hydrophobic, which is water-hating, and hydrophilic, which is water-loving properties. Therefore, they are used in non-staining, like clothes, carpets, also in food items for oils, as well as fire suppressants, such as that in firefighting foams. And as a result, because they're so used daily in our lives, we find them in water all across the country. Now, in this map, you might be thinking, wow, this is such a small amount, but in reality is that these hydrological units are very large, and we're still missing a lot of data. So our current adsorption technology is not really equipped right now to remove PFAS. If you think about your Brita filters that you have at home, we have those little black dots that you find every so often. Those are called activated carbon. These are usually made from coconut shells, and they're very cheap and affordable. What allows them to help filter our water is that they have these little pore spots. As you can see on our activated carbon, they have these little parts where if impurities get trapped, they get stuck inside. However, if you want to reuse these, it's a little bit more difficult since tap water is relatively clean. If we're thinking about water that is very contaminated, it has a more difficult time being purified with this type of filter. So this is where corn-based cyclodextrin polymers come in. Cyclodextrin polymers are made from soluble cyclodextrins, and these are macrocycles of sugar. These are 7 of them in total, and they sort of go around and form this cup shape. This cup shape also has what we call crosslinkers, which I will refer to as CLs, on these little cup shapes in order to make it a polymer. We need it to be a polymer because otherwise it would just dissolve in water, and we can't really remove things that are insoluble in water. So PFAS, they have an easy entrance into the cup because of their linear shape. As such, it allows it to get trapped inside. However, if these PFAS were a different shape, so if they were any smaller or any larger, they would either wriggle around and fall right back out, or be too big and not fit inside. So let's pretend we are all contaminants. So as a contaminant, we all have clothes on, and we can think about this as the cyclodextrins that we sort of put on ourselves. Our clothes fit for the most part, but in order to make some of our clothes fit really well, we might want to put a belt, which is what these cross-linkers are used for. And this allows us to sort of function as a whole so that we are moving as one unit with our clothes properly on, just like a contaminant would inside these cyclodextrin polymers. So we are removed as a single unit. However, like clothes and like belts that we try to put on, not all sizes fit all of us. So when we have one example of one cyclodextrin polymer that we've used, one specific type of cross-linker, using one of the PFAS compounds, PFOA in this case, we have found an 85% removal, which is pretty good. But if we take another compound, PFOS, and try using the same exact cross-linker, we only have 65% removal. That's just not enough. So what if we compare this with a different cross-linker? We actually found for this type of cross-linker, it has 95% removal, which is a lot higher. So in closing, PFAS, they're all around us, used in our daily lives. We also have adsorption technologies such as the activated carbon inside your Brita filters, as well as novel polymers like the cyclodextrin polymers that come in all different types of cross-linkers that we could possibly use to treat it. We must take also into consideration that these PFASs, because they're so diverse, just like people, they have different sizes, shapes, and somewhat of a different personality for each one of them. They all require a different way of treatment. So as we go further into looking into adsorption technology, we want to also remember that in order to figure out some of these problems, something as simple as drinking water, which everyone should be entitled to have, we have to look for the research scientists and the people around us to find better solutions. Thank you.